All right, welcome to Chain Rule Day 2. So we are going to find a few derivatives here. So it's just going to be applying the chain rule that we learned about in our first lesson to a few different problems, and then we'll move on and do some applications with it. Okay, so first one, we have this is to the 1/3 power. If you want to rewrite it, you've got 4x squared plus 7x to the 1/3 power. So the power rule is going to be our first step. Take the derivative of the outside function first. So I multiply by 1/3. I keep the inside part the same. I subtract 1 from the exponent. So I get negative 2/3. And then I want to multiply by the derivative of the inside, which is 8x plus 7. All right, don't leave any negative exponents as part of your final answer. So you're going to move that down to the bottom. You get your 8x plus 7 on top. Then you have a 3 times 4x squared plus 7x to the 2/3 power. All right, second one, I definitely recommend rewriting this one, sine to the 4th. Remember, that is sine of x cubed. Then that whole thing is raised to the 4th like that. So that allows you to easily visualize the power rule being the first step. So multiply by 4, keep the inside part the same, subtract 1 from the exponent. Then you're going to multiply by the derivative of the inside, which is cosine. Keep the inside part the same there. And then you're going to multiply by the derivative of the inside of that, which is 3x squared. Simplifying, 3x squared times 4 is 12x squared. Then you have a sine cubed of x cubed, and then a cosine of x cubed. All right, similar problem for part C. Go ahead and try this one on your own and then unpause the video and see how you did. All right, so I'm going to rewrite this one, tangent of 5x cubed. And so the derivative, y prime, is equal to 3, power rule first, tan of 5x squared, multiplied by the derivative of tangent, which is secant squared of 5x, multiplied by the derivative of 5x, which is 5. So I end up with 15 tan squared of 5x, secant squared, 5x. All right, last one here is pretty similar to what we did here on our day 1 notes. It's actually almost the exact same problem. The only difference is that one has a +1 instead of a +2. So if you want the quotient rule version of this, go watch this video, right? And you'll see how we did that. So I'm going to do this one a little differently, just so we have 2 different methods here. So I'm going to rewrite this one as 5x multiplied by x squared plus 1 to the negative 1/3 power. So now instead of using the quotient rule, I'm going to use the product rule. So f prime of x is equal to, so I'm start with the derivative of 5x, which is 5, multiplied by x squared plus 1 to the negative 1/3. Then I'm going to do plus, and I'm going to keep the 5x this time and multiply by the derivative of this thing. So start with the power rule, negative 1/3, put it in parentheses, times x squared plus 1, keep the inside part the same, to the negative 4/3, because I subtract 1, which is subtracting 3 over 3. So negative 4/3, and then I remember to multiply by the derivative of the inside for the chain rule. All right, we're not allowed to leave negative exponents, so we're going to move this to the bottom, 5 over x squared plus 1 to the 1/3. All right, and then here we get 5x times 2x is 10x squared divided by 3 times x squared plus 1 to the 4/3. All right, I'll need to get a common denominator so I can combine these together. So this one will need to multiply by 3 to match that 3, and then it also needs to multiply by x squared plus 1. Okay, that's to the first power because I want to add the exponents together, and 1 plus 1/3 is equal to 4/3. So I'm going to multiply the numerator by the same thing, 3 times x squared plus 1. All right, so I end up with 3 times 5 is 15 times x squared plus 1 divided by 3 times x squared plus 1 to the 4/3. And then this one I didn't do anything to. And then you can combine like terms to get your final answer. So this is 15x squared plus 10x squared is, let's see. I feel like, I messed up. All right. Just nothing big, nothing major. So 5x times 2x is 10x squared. That negative. All right. I made it a positive. So instead of this being plus, this should be a minus. Just a quick fix there. Fix it down here too. Okay. So now we have the right sign there. So now we have 15x squared minus 10x squared, which is equal to 5x squared. And then we have 15 minus 0, so just plus 15. Then my denominator is 3 times x squared plus 1 to the 4/3 power. All right, so you can kind of decide whether you think the quotient rule is easier or the product rule is easier on that one. All right, so I mentioned some applications we're going to do. So one of the applications for this is to write an equation of a tangent line. All right, so remember, to write the equation of any line, you need to know a point and you need to know a slope. So we were given the point, -1, 9. So all that we have to do is find the slope. Calculus, we find the slope by doing the derivative. So y prime is equal to, multiply by 2, keep the inside part the same, subtract 1 from the exponent, so it's now a 1, and then multiply by the derivative of the inside. Okay, we need to find the slope at this point, so we're going to plug in the x coordinates. We only need the x coordinate because we only have x's over here on this other side. So I get 2 times -1 cubed plus 5 times 6 times -1 squared. All right, so that's 2. This is -2 plus 5 is 3. And this is +1 times 6 is 6. So that's 6 times 6 is 36. All right, so the equation of my tangent line is y minus 9 is equal to 36 times x plus 1. Leave it in point slope form. All right, find the points where f has a horizontal tangent. So remember, a horizontal tangent is where f prime is equal to 0. Horizontal lines have a slope of 0, so we set our derivative equal to 0. So step 1, find the derivative. Okay, you could do it like we did that last example, not last one, but the where I made it a negative exponent, we did the product rule. Okay, or you can do the quotient rule. I'm going to go back to the quotient rule for this one. So f prime of x is equal to low d high. So low is 2x minus 1 to the negative, not negative, to the positive 1/2 power, times the derivative of the numerator, which is 1, minus high d low. So high is x, derivative of the denominator. Start with the power rule. 1/2 times 2x minus 1 to the negative 1/2, and then multiply by the derivative of the inside, which is 2. All of that's divided by my denominator squared, and since it's inside a square root, you can just get rid of the square root. All right, so I have to set this thing equal to 0 and solve it, so definitely going to be helpful if I simplify this. So this one is already simplified, just going to get rid of that 1, and it's minus, not plus there. Okay, so this one I have a negative exponent. My 2 and 1/2 cancel out, so I end up with an x on top, and then 2x minus 1 to the 1/2 on bottom. And then I have my big denominator, which is 2x minus 1. All right, I want to cancel out my complex fraction here, so I'm going to multiply the numerator by this denominator right here, 2x minus 1 to the 1/2 power. And that means I need to multiply my big denominator by the same thing. All right, so this is going to distribute all the way over here, and 2x minus 1 to the 1/2 multiplied by 2x minus 1 to the 1/2 is 2x minus 1 to the first power. Don't need to write it. This thing times this thing, the denominator cancels out, and you just get minus x. And then my big denominator is now 2x minus 1 to the 3/2 power. First power plus 1/2 power. Simplify, and you get a derivative of x minus 1 over 2x minus 1 to the 3/2 power. All right, so we have to set our derivative, f prime of x, equal to 0. And when you set a fraction equal to 0, that's the equivalent of setting the numerator equal to 0. So that means that x minus 1 has to be equal to 0, and so we get x is equal to 1. Okay, this did say points. Points imply an x and a y. So we found the x coordinate, plug it back into the original equation to find the y coordinate, f of 1. So that's 1 over the square root of 2 times 1 minus 1. So that's 1 over, that's 2 minus 1 is 1, square root of 1 is 1, 1 divided by 1 is 1. So we have a point, 1, 1, and that's our answer. Find the points where f has a horizontal tangent. So let's write this out as a sentence. F has a horizontal tangent at 1, 1. And we know that because f prime is equal to 0 at that point. All right, next thing we're going to do is find the second derivative. So this is where you find the derivative of the derivative. So you're going to find the first derivative, whatever that is, you're going to take the derivative again, and that's going to be your second derivative. All right, so first derivative, f prime of x is equal to, power rule first, multiply by 3, we get 12. Keep the inside part the same. Subtract 1 from the exponent, and then multiply by the derivative of the inside. Simplify, you get 24x times x squared minus 5 squared. Second derivative. All right, so we label this f double prime of x. F double prime. All right, so this one's going to require the product rule because we have a function times a function. We did not have to do the product rule on the first derivative because this was a constant in front. Okay, but once it becomes something with an x in it, then you have to treat it as a function and we have to do the product rule. Okay, so derivative of 24x is 24 times x squared minus 5 squared. Plus, keep the 24x, multiply by the derivative of x squared minus 5 squared. So that's power rule first, 2 times x squared minus 5 to the first power, multiplied by the derivative of the inside, which is 2x. All right, let's simplify. 24 times x squared minus 5 squared. And then 2x times 2 is 4x times 24x is 96x squared times x squared minus 5. All right, these both have an x squared minus 5, so I'm going to factor that out. X squared minus 5. So that'll leave me with a 24 times x squared minus 5, because I still have one more left over there, and then just plus 96x squared. All right, we can combine some like terms here. So I get x squared minus 5 multiplied by, this is 24x squared plus 96x squared. 24 plus 96 is 120x squared. And then 24 times negative 5 is negative 120. All right, so these have a 120 in common. So I'm going to take 120 out to the front, and I'm going to move over here a bit. All right, so I'm going to get 120 times x squared minus 5 times x squared minus 1. Okay, there's a little bit more you can do. There's a lot of scenarios where we want to set even the second derivative equal to 0, as you'll see in a future lesson. So if I had to set this equal to 0, this is a pretty good stopping place. Like if you got your answer to this form right here, you're in pretty good shape, even if you have to set it equal to 0. But we could do a little bit more with this. We can do a little more factoring. So I just want to go over that so you're aware. All right, so like x squared minus 1, hopefully you recognize that. That's a difference of squares. And so you could write x squared minus 1 as x plus 1 and x minus 1. And then you have your x squared minus 5. All right, and then this last step is really an extra one, but it's nice to have this in your mind because it's helpful sometimes. So x squared minus 5, in your previous classes, you wouldn't have called that a difference of squares because 5 is not a perfect square. But the numbers don't actually have to be a perfect square to do a factoring like this. Okay, so we can actually factor x squared minus 5. So we have our 120, we have our x plus 1 and our x minus 1. Then x squared minus 5 factors into x plus something and x minus something. Okay, and just think about, like, how did we get the somethings for this one? Well, the square root of 1 is 1. So like if you multiply 1 times -1, you get -1. So think about like, what can I multiply? This times this will equal 5. All right, well, it's always the square root of that number. So you get x plus the square root of 5 and x minus the square root of 5. Multiply positive square root of 5 times negative square root of 5, and you get -5. Okay, so you can even factor those that are not perfect squares by using a square root. All right, then if you had to set this equal to 0, you don't have to do any more work now. You can just say what the answers are: -1, +1, negative square root of 5, and positive square root of 5. If you were to graph the second derivative equation, any of these versions that we got here, you would see the x-intercepts are those 4 numbers we just identified. So I just want to go over a little factoring there. Miss Nancy's class has these TI-89s, and they can do that. You can do it on our Inspires. If you have a TI Inspire CAS version, you can do this, but our CX versions cannot. All right, so try that out on your CAS if you have one. Hope you all enjoyed the video, and I'll see you for the next one.